Hey folks, just checking if I'm audible. Yeah, I guess I'm live now. Okay, just checking if everything is all right. Just give us a couple of minutes. We'll start just 2 minutes past 7. So just let's wait for 3-4 minutes and see how things turn out. So let me also just check if everything is all right on YouTube, if everything is working as expected. 4 minutes. Okay. Yeah, I see no issues here. Yeah, things seem to be good. Okay. Yeah. So today we'll solve another set of 15 problems, the practice problems that we shared with all of the students, on last Wednesday, or I think Thursday morning. So today is Saturday. So just like every other time, this is our Saturday evening session where we'll go into solving the problems. Again, today we'll solve lots of problems around basics of recurrence relation, basics of asymptotic notation, and also a little bit of merge sort. So yeah, I'm just waiting for everyone to join. Just checking if Naveen, you have informed everyone, right? Okay, sounds good. So just waiting for everyone to join. We've just sent an SMS also, asking them, informing them that this would start in a couple of minutes. Okay. Okay, sounds good. Okay, I'm just waiting again. So while we wait, let's just again. I have Naveen and Subbarao here with me, who will be helping me through the live session. And thank you for some of you have sent us feedback about the last live session. Thank you very much. Thank you for your kind words. And it's very encouraging when we hear constructive and critical and encouraging feedback from our students. Of course, please also suggest us. You could email us and let us know how we can improve these live sessions better, because we're constantly looking to improve these live sessions and the whole course itself. So some of the students have already given us some suggestions on how to improve it. We're trying to incorporate that even into our content. Like, we're doing many more solved problems right now than we initially planned, because we felt for students to see how typically somebody who is fairly well versed solves problems, and also showing them that problem solving is not rocket science, it's actually simple, boosts their confidence. And we're also including more and more practice questions as we progress. So yeah, so let's get started then. I think we are 1 minute into the 7 p.m. Let's wait for maybe 30 seconds or so and get going. So yeah, thank you for your feedback. And in any way we can improve the course or improve these live sessions, please do let us know. And we'll try our best to accommodate and try to loop you in and try to change the course accordingly. We're always open for both criticism, as long as it is constructive and not trolling, and of course suggestions, because that's the only way we improve. Even for Applied AI course, which is our flagship course, we have learned a lot from the thousands of students across the world who have given us a lot of feedback on improving the course. So looking forward to more of that feedback, so that we constantly improve. We do what students want, what is better for everyone in the ecosystem. Okay, so having said that, let's change screens. I'll take myself away from this and focus more on content. Let me just share the screen. Okay, so going into screen share mode. Okay, so these are where my questions are. I'll try to solve all of them. Any questions or anything that I've majorly missed out, please do let us know in the chat window. Naveen and Subbarao will help us, will communicate that information to me, and I'll try to solve as many as possible. I'll be taking a few water breaks because this is the second live session today, so slightly exhausting. Just bear with me. Okay, folks, so let's get into the crux of it. Of course, so those students who have taken these, again, this is a practice test platform. We have tried to mimic exactly or very close to what GATE has, right? This is the practice test platform that many students have taken their mock tests for GATE 2019. And this is a pretty decent platform, very close to how the GATE experience is. But the questions would be randomized. So you may not see, when you're practicing these questions, the order of questions that you see would be different from the order of questions that I am answering, because we randomize these questions, right? So Let's go into the first question here. The first question here is, consider this equality, right? What do you have here? Summation I goes from 0 to n I cube. So what does it mean? It means 0 cube, which is 0, plus 1 cube, plus 2 cube, plus 3 cube, so on so forth, up to n cube, right? That's what we have. Okay, let's assume this is equal to x, right? Which of the following choices of x is correct? Okay, that's a good question, actually. That's a pretty good question, right? Which of the following choices of x is correct? Let me change the colors here. Okay, this color looks good. Okay, this is deep red. Let's also use deep red. Okay, so which of the following options is correct for x? So let's see. So you might have studied this when you were in 11th or 12th class, right? Sum of cubes of first n numbers, right? So those of you who have forgotten it, the answer is very simple. The sum of the first n cubes, because 0 cube is 0, you can just ignore this. This is nothing but n into n plus 1 by 2 whole squared, right? So the way I recall this, the way I remember the sum of cubes is, you take, so what is the sum of all the numbers up to n, right? Sum of all the numbers up to n is n into n plus 1 by 2, right? This is the sum of all the numbers from 1 to n, right? Simple arithmetic progression. Now, if I square this term, I get the sum of cubes, okay? So very simple. Once you know this problem is trivial, okay? So what is this? What do I have here? I have n square, n plus 1 squared by 4. Now, what is this? Okay, this obviously, we know, of course, I can expand on n plus 1 square and all of that, but you can quickly see that what we have here, okay, this is our x. This x is theta of n power 4, makes sense. Because look at this, what is the largest exponent I have? The largest exponent I have is n square, and of course, n square here, right? So this will end up being in some n power 4, some constant into n power 4 plus some constant into n power 3, so on and so forth. So this is a polynomial of degree 4. Okay, and some of these could be zeros, right? So, but a will not be 0. So this is a polynomial of degree 4. And we have studied in the course that polynomials of degree 4 are of obviously theta of n power 4. So this option is right. What about theta of n power 5? This is not right, right? Because theta basically signifies a tight bound. Remember, theta signifies a tight bound. Theta signifies a tight bound, while big O signifies an upper bound, right? We have also discussed this extensively. Omega represents a lower bound. Okay, we've also shown this graphically in the course videos, also the free videos, right? So certainly it is not theta of n power 5, right? This is not true. Is it big O of n power 5? Yes, that seems to be right, right? Because your n power 4, look at this, n power 4 is upper bounded by n power 5. Because if you think about it, n power 5 grows faster than n power 4. So obviously, because n power 5 grows faster than n power 4, you can always write n power 4 as big O of n power 5. That by the definition of big O, right? So this statement is also right, that x is big O of n power 5. What about the last one? The last one, because theta represents the lower bound, you can also say n power 4 is omega of n cube, because n cube certainly grows slower than n power 4, right? From the definition of omega. Okay, we have seen this in the previous practice sessions also, right? So very simple. So this is also true. So now let's see the options. So the way I typically solve problems is, I typically solve the whole problem myself and then look at the solutions. Of course, there is some disadvantage that you might have to compromise on speed there. So only 1, certainly not. Only 2, certainly not. 1 or 3 or 4, but not 5. This seems to be the right choice, right? So the other one is 2 or 3 or 4. No, 2 is not right, right? So this can't be the option. So the right option is C here. Right? Very simple. The two pieces of information that you need to know, that sum of cubes is this formula. The moment you know this, and you know the definition that theta is tight bound, big O is upper bound, omega is lower bound, the moment you know that, this problem is literally like, you can actually solve this in 30 seconds, while I've taken longer period of time to explain you in detail, right? So this question is straightforward. So let's go to the next question. Okay, so, okay, this is the next question, right? Right here. This is an interesting question. I really liked solving it. So what I typically do is I try to solve all of these questions before the live session and write notes for it so that I don't make mistakes in a live session. So let's see. So you have, again, by the way, we have the order of functions, right? I hope you all recall that. So let me just open the page for order of functions also. So I have this. Okay, this is the Wikipedia page, right? We have discussed this in the course videos also, right? So this is very useful. This order of functions table on Wikipedia for big O notation is very useful. If you can remember this, again, by solving lots of problems, this will become second nature to you. Right? We also discussed this in lots of detail in the course videos, right? So if you know this order of functions, solving most of the problems today would just be simple algebraic transformations. Okay, so let's keep it handy because we would need it. Okay, so let's see what we have now. So this can be written as n power half. So we have n power half. This is 10 power n. Now, if you recall the order of functions, if you recall the order of functions, your c power n, where c is greater than n, has a very high, is basically very fast growing function. The only other fast growing function is n factorial, right? So what we have is 10 power n, which is c power n, right? So let's go here. Okay, so this is like c power n, right? So 10 power n grows very fast. This is n power half, n power 1.5. Obviously, n power 1.5 grows faster than, so I'm just trying to order these things, right? So I'm trying to order it in such a way that the fastest growing functions or asymptotically increasing functions are on the right. Obviously, n power 1.5 grows faster than n power half, certainly less than 10 power n. Again, if you're not convinced with that, let me just show you this. Okay, let me just show you here. Okay, this is very important. So look at this. Look at what we have here. This is, okay, look at this. You have n power c here, where c lies between 0 and 1. So n power half will lie here, and order of n is here. So what we're doing here is we're multiplying both of them. You have n square here and n power c here, where c is greater than 2, right? So what we have right now is n power half. N power, let me open that up. Okay, so what we have is this. So n power 1.5 certainly grows faster than n power half, but slower than 10 power n. Again, the order of functions is the key thing here. If you can recall, or if you can, I mean, it almost becomes second nature. I don't remember it by heart, but I almost know it instinctively now after solving so many problems. So this is taken care of, 10 power n, this is taken care of. Then this is an interesting term. Okay, let's try to understand this. Again, we'll come to this. What is this? This is n power 5 by 3. What is 5 by 3? N power 1.66, right? So obviously, it's straightforward that n power 1.66 grows faster than, this grows faster than n power 1.5. So these four have been placed in the right locations. The only confusion now is about this function. Okay, so that's the tricky part. Now let's see what to do with this. Actually, I think, okay, this option is there. This option has everything ordered properly. The only confusion is between these two, and there is none of these. So you have to be very careful. There is an option called none of these. So you have to be careful, right? So let's take this function now. Okay, what is it? 2 power. Okay, let me write it. Log n. Okay, since it is log base 2, let's write it as lg. Okay, just a simpler notation there. So 2 power lg of n, square root of this term. It's not square root of n. It is square root of the whole log. Lot of people make a mistake here. Okay, so this power half. Now let's try to compare this. Okay, so let's try to compare this versus your n power half. Okay, we'll take the smallest one first. Let's try to compare these two first. Okay, if we want to compare both of them, let's take log on both sides, right? Let's take log on both sides. What do you get if you take log on this side? Since it is 2 power something, okay, log base 2 of 2 power a is equal to a. Simple property of logarithms, right? Again, we have used all of this in the previous practice test. We're just reusing the same concepts here. So this would become log n power half. Okay, this one versus, if you take log of, what happens? It becomes log half of log n, right? This becomes half of log n. So if you think about it, if you imagine log n as x, let's just say log n equals to x. What is this term? This term is x power half. What is this term? This is half of x, power 1. Okay, look at this. If log n is x, so this is like square root of x, and this is like x. We know that square root grows slower than x itself. Look at this. Again, we can go back to the, again, we can go back to the order of functions and see that, right? If you go to the order of functions, so if you go to the order of functions here, okay, so you have n power c here. Okay, if our n is x, c lies between 0 and 1. So this becomes x power half. This becomes x power 1. So from the order of functions, we know that x power 1 grows faster than x power half, right? From the order of functions. Again, it's important to remember this or be able to recall this quickly, right? So, okay, where am I? Okay, let's go front. Okay. Uh-oh. Where are we? Okay. I think I lost that slide. Just a second. Let me try to grab that. Oh, here we are. Okay. So we have x power half versus this. So obviously this grows faster, which means this must be growing faster, because what we have done is basically taking only logs on both sides and simplifying it, right? So this must be growing faster than 2 power log n base this thing. So in the ordering, you would have 2 power square root of log n. So this grows slower than this, which grows slower than this, which grows slower than this, which grows slower than this. We don't have that ordering anywhere. So the right answer here is none of these, right? So the trick here, the very important aspect or the trick here is to be able to take logarithms and be able to compare them. The key is order of functions. See, if I have to summarize this whole thing, right, this whole exercise, it all boils down to order of functions, knowing properties of logarithms and exponentiation. Right? 2 power x is called exponentiation. If you know these basic properties, you can solve most of these problems. Okay? It's just simple algebra, not at all rocket science. Okay, so now let's go to the third problem. Okay, seems very similar. So let's solve it. Okay, so what do we have now? Again, sort the following functions in increasing order of growth. Assume LG means log base 2. Very good. Okay, so we know that. Okay, let's see. Oh, this seems somewhat funny. What does this mean? 2 power log n base 2. What is this? This is nothing but n. Because we know that 2 power log n base x is x itself by definition. Right? By definition, this is x. Because if you take log on both sides, what do you get? You get log x equals to log x. Sorry, base 2. That's what I meant here, not n, base 2. Sorry. Okay. So this is like straightforward. So this is a tricky way of saying n, right? So what do we have here? We have n power half. Okay. We have log n. Okay, we'll come to log n. We have 2 power n. We know that 2 power n certainly grows faster than n power half. So these two are taken care of. We have n. So this is nothing but n. We know that n grows faster than n power half, but slower than 2 power n. So this is also taken care of. What about log n? Right? This is a good one, right? And again, you can go back to the order of functions and see that log n grows slower than n power half. Okay, if you want, I'll show that to you. If you want it, I'll show that to you. Okay, again, these are important concepts. So for example, if you see, look at this, you have log n here and n power c, where c lies between 0 and 1. So your n power half is here. Your log n is here. I'm sorry. So log n grows slower than n power half because this table is ordered in an increasing order. Okay. Those of you who are not a registered students can still go to Wikipedia or search for big O notation, order of common functions, Wikipedia. You'll get this page. Okay. Very simple concept. Okay. So this question, okay, what is the answer? I think I didn't tell you the answer. I think I wrote down the answer here. Okay. So this is the answer. So what is the option here? Log n power half. No. So where is log n? So I have log n power half, 2 power log n. Oh, 2 power log n is nothing but n, right? So this is nothing but 2 power log n, right? So the right answer here is D. Okay, so that's all it is. Okay, so third question also done. Let's go to the fourth question here. Oh, this is a fun problem actually. I like it. Okay, so for this problem, let's start solving it. Okay, so you have 4 parts. Again, the question here is for each group of functions, sort the functions in increasing order of big O complexity. Again, same, very similar. Again, you typically tend to see these problems very often in GATE, right? And hence we've given so many practice sessions. Okay, so let's take this. Let's take each of these. Okay, this is a slightly tricky one. That's why we put it here. Let's start we can start from this, right? Let's start with this. What is this? So if you say I equals to 1 to this I plus 1, what is this? This is basically 2 plus, think about it, I plus 1. If when I equals to 1, this becomes 2. 2 plus, 3 plus, so on and so forth up to n plus 1. That's what it is, right? This is basically, we know that sum of all the numbers from 1 to n plus 1, right? We know this. We know that this is equal to n plus 1 into n plus 2 by 2. We know this. There is just one missing here, so I'll just subtract 1 from this, right? So this is nothing but order of n square. So your f4 of n is nothing but order of n square. Okay, because it is basically the sum of numbers with small twist here. Okay, so f4 is taken care of. Now, one thing you'll notice here is you have some 2 power something here, you have 2 power something here. Okay, and you don't have 2 power here, you have n power square root n. Now, how do you compare all of them? That's a tricky question actually. Okay, the easiest trick here is to convert all of them into the same 2 power n structure. Okay, obviously I know that 2 power n grows faster than order of n square. So obviously f2, I know if you look at the final order, I know that f2 grows faster than, okay, in the final order, certainly f2 grows faster than f4. That is guaranteed. Okay, but what about f1 and f3? Where do I place f1 and f3? That's the question here, right? So let's take this. You have 2 power n here. So if I try to convert this and this into 2 power n structure, then I can compare all of them. So that's the trick here. So we'll employ the trick here. Let's see how to do it. Let me change the colors a little. I'm bored with using the same red color. So let's look at this. Suppose if I take log of this, or I can rewrite this. What do you have? N power 10, 2 power n by 2. Okay, how can I write this? Can I write this as 2 power log of n power 10 multiplied by 2 power n by 2? They both are same because 2 power log of n power 10 is nothing but n power 10. That's what I have here. I'm rewriting n power 10 as this structure. When I have this structure, look at this. When I have this structure, right, I'll try to simplify this. This I can rewrite it as log of n power 10 is nothing but 2 power log of, right, 10 into log n, sorry, 10 into log n, right? That's what I have. 10 into log n plus, because this is the multiplication of these two, plus n by 2. So I can write f3. So let me write f3 here clearly. So what is my f3? My f3 is 2 power, let me write it clearly, 10 into log n plus n by 2, right? This is my f3. So the trick here is I've converted n power 10 using this hack. Using this hack, I've converted the whole f3 function as 2 power something. Okay, so now let's go to f2. f2 is anyway 2 power n, straightforward there. Okay, so we know f2 is straightforward. f2 is straightforward there, staring at us. So f2 is 2 power n. What about f1? Let's try to simplify f1 now. f1 is n power root n, right? I can write n as 2 power log n. This whole thing power root n. Why is it so? Because 2 power log n is n, right? So this is the hack. And because of the way logarithms and exponentiation works, I can rewrite this as 2 power. I can take this and multiply it here, root n log n, right? This is simple properties of exponentiation. So what is my f1 now? My f1 is equal to 2 power, okay, square root of n into log n. Now look at this. Now my f1, f2, f3, all of them are in 2 power sum format. This is 2 power n. This is 2 power something. This is 2 power something. Now, if I want to understand the ordering amongst them, since all of them are 2 power something, I can simply compare these exponents, right? For my f2, what is my exponent? My exponent is n. For f3, what is my exponent? 10 into log n plus n by 2. What is the exponent for my f1? It is square root of n into log n, right? So now let's see. Now let's see the order. Obviously, n grows faster than log n plus n by 2. Obviously, right? Because look at this. I can write n as n by 2 plus n by 2. This n by 2 and this n by 2 is the same. And I know that n2 grows faster than log n, right? So obviously, f2 grows faster than f3. Okay, so what do I have now? F2 grows faster than F3. Okay. And obviously, since F3, right, since F3 also has 2 power something in the exponent, 2 power n is there here. Because I have 2 power n in the exponent, it obviously grows faster than my F4. So I have this partial order right now. Let me rewrite it. I have F4, F3, F2, right? So I have F4, F3, F2. I don't know where F1 should be placed now. Okay, let's look at F1. Okay, so what is there? What is the exponent of F1? I know that F4 doesn't have any exponent. So F4 certainly is going to be the slowest growing. Okay, so F4 is anyway going to be the slowest growing because it doesn't have any exponentiation function. Now my F1 can be placed here, it can be placed here or here. So let's compare F1 with F3 now. What is F3? F3 is log n plus n by 2. Okay, what is this? This is n power half into log n. Okay, let's look at this. Okay, let's actually just compare these two. Okay, so what is this? What do I have here? I think I should get a new slide. Okay, so let's, okay, else I'll try to solve it here. I'll just change the color. Okay, so I have n by 2 plus log n here. I have square root of n into log n. Okay, so can I write my, look at this, can I write my n by 2? Okay, this is basically n, right? Just keep the constant half away. I can write n as n power half into n power half into half, right? I know that this n power half and this n power half are the same, so they must be growing at the same rate. Now here I have n power half and log n. I know from the order of functions that n power half grows faster than log n, right? So right now I haven't even touched the second term. I haven't even touched it. I'm just using the n by 2 term, and half is anyway constant. So from this simple argument that this n power half cancel out if you're trying to compare both of them, and this n power half grows faster than log n, which means F3 must be growing faster than F1. F3 must be growing faster than F1. Yes, which means F1 must be here, right? So this is a tricky question. It's I would call it slightly on the harder side. It's not very hard, to be honest. So what is the right answer? F4, F1, F4, F1, F3, F2. So this is the right answer, right? So here the key lesson here is when you have these crazy exponents, try to convert everything into the same base using this hack that 2 power log n is equal to n. Okay, use this hack to solve this problem. Now what I've done here is I've converted F1, F2, F3 into 2 power something. The moment I convert all of them to the same base, I can just compare the exponents, thereby solve it much more easily. That's the tricky part here. If you know this trick or if you know this strategy, you can employ it everywhere you go. Okay, so it's a good question, very good question actually. So now let's go to the 5th question. Okay, this seems to be a straightforward case, at least looks like, but let's see. Which one of the following is the recurrence relation for the best case time complexity of merge sort algorithm for sorting n numbers where n is greater than or equal to 2? In the recurrence relations given below, C is a constant. Very good. So in the merge sort, we know, well, how does merge sort work? We have an array of size n. We break it into 2 arrays of size 2, right? So we have an array of size 1. We break it up into 2 arrays of size n by 2. And we recursively sort them and then we merge it. That's the core idea. Whether it is the best case or worst case, we keep doing this. So it is 2 times n by 2 plus what is the time complexity to merge? We have discussed this extensively in the course and we have also detailed this. The time complexity to merge both of them is again order of n, which means it is Cn, right? Straightforward question, straightforward answer. Actually, we have done this analysis in lots of detail in the course videos also. This is like textbook question. Okay, too simple, too trivial, to be honest. Okay, next, let's go to the 6th question. Okay, this is a tricky question because I got thoroughly confused when I was trying to solve this question. Okay, by the way, this is actually a GATE question. This is a GATE question, I think, from 1999. This was also asked, if I'm not wrong, in ISRO entrance exam or ISRO's recruitment exam in 2015, if I'm not wrong. But this question is very confusing, actually. Because I tried to solve it, there's a lot of confusion here. Thankfully, GATE questions nowadays are much more rigorous and well written. So it says, if one uses straight two-way merge sort algorithm to sort the following elements. So what all elements I have? I have 20, 47, 15, 8, 9, 4, 40, 30, 12, and 17. Let's assume this is what I have. Okay. It says I'm using a two-way merge sort algorithm. Two-way merging, not k-way merging. We have discussed k-way merging in the course videos. Then the order of the elements after the second pass. This is something that I'm not convinced with, because because typically we learn merge sort from a recursive standpoint, and the word pass is typically used for iterative algorithms. So I got thoroughly confused what they meant by second pass, because typically if you look at any major textbook or even Wikipedia for that matter, merge sort is implemented typically using recursion. Of course, you can also implement it using iteration, but that's not the standard one. And of course, you typically convert recursion to iteration. Now, while doing this, I got thoroughly confused. And like, frankly speaking, I think this question could have been framed much more cleanly. Okay. But then I said, let's solve it anyway. Imagine if such a question comes, you don't want to leave it, right? So I said, okay, one way to solve this problem is, let's talk about merging these. Because anyway, what happens? The merge sort basically recursively breaks these things into single element arrays, right? It will break the whole tree. It will break the whole tree into single array elements, right? And I think we have 10 elements, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now let's assume I'm merging both of them. Okay, when I merge both of them, what do I get? I get 20, 47. When I merge both of them, I get 8, 15, because I'll try to merge them such that the sorted order is here. When I merge both of them, I get 4, 9. When I merge both of them, I get 30, 40. When I merge both of them, I get 12, 17. So I assumed here that second pass basically means they're considering this merging as first pass. Okay, that's how I understood it to be, because there is no other way I could interpret this. So with this interpretation, I went ahead. Okay. Now if I start merging them, okay, of course, I can merge these two, and since this is one element, I can leave it here. Now what do I get? I get 8, 15, 20, and 47. Here, what do I get? I get 4, 9, 30, and 40. And here I get 12 and 17. Is this so? Because this is the end of second pass, as they call it, right? So this option is there somewhere, right? 8, 15. So this option is here. So if I have to answer this question in an actual exam setting, I'll probably answer it here. But there's a bug with this question. Okay, let me tell you the bug that I thought of. Why should I merge these two like this? What stops me from saying I'll just copy this, I'll merge these two like this? I can implement merge sort the way I want, right? My implementation is my specific thing. Instead of merging these two, and these two, what if I merge it differently? What if I merge it, I just copy this, I merge these two, I merge these two, then the whole order will change. Then my second iteration will look like 20, 47, merging of these four, which is 4, 8, 9, 15, merging of these two, which will be 12, 17, 30, and 40. I can implement merge sort the way I want, right? And hence, I think this question is not very rigorous. But if a question like this is given, you try to find out which option is the most suitable option. Okay, so because I struggled, because typically the way I solve questions is I don't look at answers. I try to solve it myself on my notebook, and I say, okay, which of these options matches closest to this? I got thoroughly confused by this word second pass and by the order of merging also. Okay, so this is a simple question, but it could have been framed better. That's what I would leave it at. Okay, so let's go to the next question. This also, okay, let's see the question. In the worst case complexity of merge sort, sorry, what is the worst case complexity of merge sort if all the elements are in ascending order? Merge sort doesn't care. Merge sort time complexity is T of n. The recurrence relation is 2Tn by 2 plus Cn. It doesn't care whether it's in ascending order or not. It recursively keeps doing it. And merge sort time complexity, we have solved these recurrence relations and we have seen that it is order of n log n. This is like a straightforward textbook question again. Okay, simple, easy. And there are some questions in GATE which are like this, mostly 1 mark questions, and they're sometimes straightforward. These are very scoring. Of course, you have to be careful to read the question carefully. Some of these questions can be tricky, and you will make mistakes if you're not careful. So just read the question. So one trick that I always do is I highlight all. I mean, this is again my personal practice, when I read a question, all the important pieces of information, you might have noticed this me doing a lot. I underline or I circle the important pieces of information so that I don't miss it when I'm solving the problem. This is my personal choice. Of course, in a GATE exam with computer, without this pen interface, it might be harder, but just make a note of it in your mind. Okay. When I wrote GATE exam, it was a paper-based exam and my paper was fully scribbled. Okay. So this is a straightforward question again. So let's go to the 8th question now. Okay. This also seems straightforward, but let's solve it. Okay. So in a modified merge sort, so the modified is the keyword here. The input array is split at position 1/3 of the length of array. The recurrence relation that represents the modified merge sort. So what? I have this big array. I break it up into n. So this array is n. I break it up into n by 3 and 2n by 3. Right? I can always merge them in cn time. Right? In order of n time, I can merge it. Right? Because merging depends only on the size of the number of elements in these two arrays. Right? This has n by 3 elements, this has 2n by 3 elements, the total elements are still n. So what is the recurrence relation here? Tn is tn by 3, makes sense because I'm going to recursively break this. 2tn by 3, no. Where is this? I think it should be what? Let's write it down. Tn is tn by 3 plus t2n by 3, right? Plus the constant into n, right? This is what it should be, right? Did I make a mistake? I don't think so. This seems right? 2 into, this is not the case, right? I think the small mistake in the options or something like that. But anyway, none of the above is, we have the option none of the above. So I'll go with this. Because tn by 3 plus 2tn by 3 is nothing but 3tn by 3. That's not the, I think, yeah. Again, I don't look at options and solve it. I solve it and then pick the right option. This is the right option and none of the above. Okay, sounds good. Again, straightforward question, simple modification. If you know the concept, this should be straightforward. Here comes an interesting question. This is actually easy but interesting. Okay, let's look it up. Okay, let's change the colors again. I'm bored with using a single color. So we have 5n. Again, arrange the following functions in increasing order of growth. Okay, big O, defining what big O is, all of that stuff. Very good. So I have 5n here, 4 log n. Okay, I know that 5 is just a constant here. I know 5n grows faster than 4 log n. Right? I know this already. I know log n grows slower than log n. Right? So 4 times log n certainly grows slower than 4 log n. So I've n power half. Okay. Now look at n power half, right? So, oh no, this is not n power half, sorry. This is a whole term here. Okay. So let's understand this. Okay. So what is this? N power half into log 4n. Okay, now I want to understand, because I know this is log, so this has to be, if you think about it logically, this function can either be here or it can be here. There are only 2 positions that it can be here, which means I have to compare this versus 5n. That's a comparison that I have to make, right? So let's write 5n as 5 into n power half into n power half, right? This is n power 1, which is what we have. So this versus n power half into log 4n. So if I'm comparing both of them, this n power half and this n power half can be cancelled out because they're the same term. So what do I have here? I have log n power 4, right? I have log n power 4 and I have n power half. Again, let's go back to the order of functions. Okay, let's go back to the order of functions. Okay, where is log n power half? It is here, right? This is c greater than 1, and this is n power half is here, right? This is log n power 4, or log, you can write it this way also, right? So from the order of functions, this is the key information that you need to know to solve this problem, right? So let's again go to that window, and yeah, so sorry. The key information that you need to know here is this grows faster now than this, which means your n power half log n power 4 is here. So this is the right order. Where do we have that? 4 log n, no, not this. This is the right order, right? So the key trick here is when you have this complex stuff, break your n into 2 parts so that you can cancel this out. You can at least cancel this term out, right? And whatever you're left with, compare those two. That's it. That's the trick or the strategy here. Okay, very simple. Once you know this strategy, these problems are straightforward. Okay, so let's go into this. Okay, so this question says a list of n strings. You're given n strings. Okay, I don't like the black color too much. Each of length n. So you have n strings, each of length n, to be sorted in lexicographic order. Lexicographic order basically means alphabetic order. Okay, using merge sort. The worst case running time of this computation is, it's a very good question actually. Okay, imagine I have n numbers. Forget about strings. If I have n numbers, what is the time complexity of merge sort? It is order of n log n. One thing you have to realize is I can compare numbers in order of one time. See, in merge sort, what do you, when you're merging stuff, right? When you're merging two arrays, you compare this first element with this first element. Then whichever is smaller, you place it into the merged sort. You suppose if this is smaller, you place it here and you change the pointer. So you're comparing and you're assuming that comparison is order of one time because they're numbers. But now what do we have? We have strings of length n. So instead of numbers here, we have strings of length n. So for strings of length n, basically it has n characters. Each string has basically n characters. Okay, so let's say H, Y, D, E, so on and so forth. It has Hyderabad to write Hyderabad, right? So each of these strings are of length n. So to compare two strings of length n and to decide which string is alphabetically before the other string, how much time does it take? You have to compare. Imagine if I have two strings, I have to compare them alphabetically. I have to compare each of these, right? Worst case, I have to compare all of them, which means this comparison takes order of n time. Right? So comparison of two strings in the worst case, because the word here is worst case. In the worst case, to compare two strings of length n, you will take order of n time. Which means what you were able to do with numbers in order of one time to compare will now take order of n time. Right? Now what happens? Your total complexity will become order of n into n log n. Right? So it becomes n square log n. Right? So this is a very interesting question. It's a tricky one. You have to be careful and understand that comparing two strings of length n takes order of n. And you have to understand that numbers we compared in order of one time. We never mentioned this explicitly when we learned merge sort. So this is a very interesting and a slightly tricky question actually. Okay. So now let's go to the 11th question. But it's a good one. I really enjoyed solving that. Okay. So now this question on the surface of it looks like crazy hard problem. Look at the numbers that are there, but it's actually easy. I'll show you. Okay. So because when I first saw it, I said, dude, what is these numbers? These are crazy. What is this? This is actually a constant. Again, the question here is sort the functions in increasing order of asymptotic complexity. There is no n here. This is a very large number. This is a very large number, but it's still a constant. Let's not forget that. Okay. So what is this? This is 2 power some constant into n. Of course, this constant is large number. What is this? This is n choose 2. This is nc2. Right? What is nc2? nc2 is n into n minus 1 by 2. Right? This is nc2 in combinatorics. This is how nc2 is written. This is order of n square. We know that. What is this? This is n into root n. Right? So this is n into root n. So what is this? N into n power half. What does that become? This becomes n power 3 by 2. Now, amongst all these functions, let's see how they grow. Obviously, n power 3 by 2 grows slower than n square. Right? We know that. Now, this is constant, right? Oh, the constant grows slowest. So f1 will grow slower than everything else as n increases, because that's a constant. I forgot. So f1 is taken care of, f3, f4 is taken care of. We know f2. This is some constant where the constant is greater than 1. Right? We know that f2, which is 2 power cn, grows faster than all of these. So what is the order? f1. What is this? Is f4, right? This is f4. What is n square? N square is f3. What is this? This is f2, right? So f1, f4, f3, f2. First option. That's all there is. Okay. So here, a lot of people look at these crazy numbers and say, oh, this is a big number. It's a constant at the end of the day. For asymptotic complexity, even if the number is large, it's just a constant, because my n can be greater than this, theoretically speaking. right? So that's nothing to worry. Let's go to the 12th question. Oh, this is a fun question. It took me a while to figure this out, and I did the brute force way, to be honest. Okay, the average number of comparisons performed by the merge sort algorithm in merging two lists of length 2 is assuming that all the elements are distinct. Okay, imagine I have two lists. One list is 1 2, the other list is 3 4. How many comparisons will I perform to merge both of them? See, I have two lists with distinct numbers. All the four numbers are distinct. So I'll just take 1 2 3 4 as an example. To merge these two lists and to create final list, how many comparisons I have to make? I have to make one. I have to compare 1 with 3. That's one comparison, right? So 1 will be done. Then I compare 2 with 3. One more comparison, right? 2 is done. Then 3 and 4 done. So 0 comparisons. So total, I had to do 2 comparisons to merge if the arrays were like this. On the other hand, imagine if the array was like this: 1 3 2 4. Right? If this was the array, how many comparisons? If these were my sub arrays that I had to merge, okay, 1 and 2 had to be compared. So one comparison. So this is done. Now I have to compare 2 with 3. That's one more comparison. 2 is done. Now I have to compare 3 with 4. So total are 3 comparisons I have to make. There is no need to make 4 comparisons anywhere. Now the question here is, what is the average number of comparisons? That's the tricky part here. So I said, I don't know. So I wrote all the possible options. I'll tell you, I literally wrote it on my notebook. 1 2 3 4. If this is the odd, if this is how my two arrays are, I need 2 comparisons. If it is 1 3 and 2 4, okay, I'm just copying this from my notebook here, okay, because it'll take me a while to actually do all of this. So then 1 4 and 2 3, again 3 comparisons. Again, you can work that out, okay. 3 4 and 1 comma 2, this requires 2 comparisons. 2 comma 4 and 1 comma 3, this requires 3 comparisons. 2 comma 3 and 1 comma 4, this requires 3 comparisons. These are the 6 options that we will have, right? So the question here is average. That's a tricky part. So I said, what is the how many options do we have? We have 6 options here. There are 6 possibilities. And what is the total number of comparisons? 3 plus 3 plus 2 plus 2 plus 3 plus 3. That is 16. So there are total of 16 comparisons that you'll make, and you have 6 such options, 6 such possibilities. So 16 by 6 is the average number of comparisons that you'll make, right? What is this? This is 8 by 3. I got the answer here, 8 by 3. But it took me considerable amount of time to solve it, because this is brute force way of solving it, literally. Then I read up. I wanted to find out if there is some way, or if there is some formula. So it seems, in general, this is an interesting thing that I didn't know before I solved this problem. The interesting thing here is, if you have lists, if you have 2 lists of size n by 2, if you have 2 lists of size n by 2, and to merge these 2 lists using the two-way merging in merge sort, if the list size is n by 2, right? Which means in our case, n equals to 4, because our lists are size 2 to each. So if you have lists of size n by 2, the average number of comparisons would be n square by n plus 2. Of course, it's impossible to remember all the formulae. I didn't know this before, but I read up and I found this. Okay. So if I knew this formula, right, I can just replace it and say n square is 16, n plus 2 is 6. So my problem is solved. But if I don't know this, I can always, actually I solved it using the brute force, to be honest. Okay. Thankfully they asked only of length 2. If they asked length 3, I had to know this formula, or I'll spend forever to solve this problem. Okay. So it's a good problem, but it's lengthy. It takes time. Okay. If you did not know this formula like me, it would take time. Okay. So let's go to problem 13. Okay. This is a good problem, and it looks crazy, but it's actually simple. I'll just take a quick sip of water and get back to this problem. Just give me a sec. Okay. So I have these 4 functions. Yes. Sorry?
Last question. 4321 is also correct.
That means 4 comma 3, 2 comma 1.
Did I miss that somewhere? One second.
4 comma 3.
Yeah.
2 comma
2, 1. Okay. Oh, I think I missed some of these options. Okay. Oh, thanks for the correction. Very good point. Okay. So how many comparisons are needed here? Let's look it up. Is there anything else that I missed out here? 1 second. So let me go to that question first. Sorry. Okay. Good catch. Good catch. Very good catch. Mahesh, very good catch. Thank you. Thank you for that correction. Is there any other option that is missing here? 2, 3, 2, 4, 3, 4. Oh, I think I forgot 4, 3. Okay, so let's see. For 4, 3, how many comparisons are needed? Okay, I missed this. Okay. So first I compare these two. So one comparison. Then I compare. So this is gone. Then I compare this with this. 2 comparisons. This is gone. So this requires 2 comparisons. Right? So how many do I have now? 18 by 7 is what I have. Oh, this looks like, is there any other option that I missed out? I'm just thinking. I actually missed out 4, 3 and 2, 1. Okay. So there is 2 here. Okay, let's see the question. Oh, okay. Folks, this is not possible. Yeah, you're right. Actually, Naveen just read the question carefully for me. The question says 2 sorted lists. Okay, so 4, 3 is not in sorted order. 3, 4 is the sorted order, right? 3, 4 is the sorted order. 2, 1 is not the sorted order. 1, 2. Otherwise, there are many more options actually.
Even we can take 2, 1 also in the beginning.
Oh, yes. Instead of 1, 2, I could have taken 2, 1 also.
3, 1, 4, 1.
The key here, that's what I was thinking because I solved this problem very carefully. I actually have 1 page of solution here. Oh, the question here. Okay, that's good. Good catch, Naveen. Good. So Mahesh, it's a very good point that you asked, and I'm glad that you asked it. So it says sorted list. By sorted, I mean it's ascending order by default, unless it's clearly mentioned. Okay. So thank you, Mahesh. You made us question that. That's good. I always want people to question us because that's the best way we all learn. Like imagine if I did not read this question, because I think when I was solving this question on my own, I read the question carefully and I think I highlighted sorted list also. But here I got confused. Okay, so thank you for calling it out. Very good. And this is how we all learn. Again, this is also a learning experience for me. Okay, folks. So let's go to the 13th question. Okay. 13th question is this. Okay, this looks crazy complex at the outset, but it's not. Let me show it to you. Okay, what is this? This is c power n, where c is greater than 1. Right, that's what it is. Okay, this is c power n, where c is greater than 1. Again, go back to the order of functions. F3 grows faster than F4. We know that for sure. Okay, because this is an exponential function, while this is a quadratic function. This is a constant. This is basically order of n. However big this number is, I don't care. Right? This grows slower than n square as n increases. So F2, I know, certainly grows slower than F4. I know F3 grows. So I'm just trying to write the order here. What about this? This is the tricky one. I have to, what is my F2? My F2 is basically, my F2 is some constant into n. What is my F1? My F1 is n power point some 999. Let's say 3 nines. I don't want to write how many 6 nines are here into log n. Very simple to compare actually. Okay, what is this? Keep the constant away for a while. I can write this as n power 0.999 or 6 nines. Okay, I'm lazy to write it. 0.001 versus n power 0.999 into log n. These both are the same. Whether it is 3 nines or 6 nines, the same thing. Now we are left with 2 parts. You are left with n power something and log n. From the order of functions, n power c grows faster than log n, especially when c lies between 0 and 1. However small it is. However small the c is, as n increases, this grows faster. Right? So from this simple fact, I can tell you that F1 grows slower than F2. So this is my ordering. So I have my F1, F2, F4, oh no, sorry. Option F1, F2, F4, F3. Yes, this is what I have. Yes. Option B. The trick here is to, again, the trick here, that's important, but the trick here is to take this. See, because at the end of the day, I had to compare F1 and F2. Right? This is n power 1. I try to find common terms between both of them and cancel out the common terms so that I can just use order of functions to solve the whole thing. That's the trick, or that's the strategy, whatever you want to call it. right? So let's go to the 14th question. Okay. Oh, this question also I got confused thoroughly, frankly speaking, because of the way it is termed. Okay. It says I have n lists. I have n lists. I have list 1, list 2, list 3, so on and so forth, n lists. Okay, of m integers. So there are m numbers here. This is list 1, this is list 2, list 3, so on and so forth, list 10. Each of these lists has m numbers. Okay. In ascending order. Very good. So these are already sorted. These lists are already sorted. M integers, all these lists are sorted. Merging these lists into a single sorted list. Merging all of them into a single sorted list. What is the time it takes? Look at this. Merging into a single sorted list. The moment I read this, I thought we'll have to merge it using k-way merge. The minute I read this, I thought, oh, this is some k-way merge. But that's not what they mean. I think this question could have been more clearly stated. Imagine if I don't have these options. Okay, because I typically don't look at the options. I look at the question first. Instead of saying this, I think if they had said, so as to avoid this confusion of k-way merge or not, if they said merging these lists using two-way merging, that would have been more clear. Okay, so here I'll assume that we will use two-way merging only. Okay, that would have been made clear, because the moment I see k sorted arrays and if I have to merge them, I think of k-way merging. Of course, I'm biased by it because I've used k-way merge in a different distributed systems application while I was working. So I have some bias there, but they could have been more clear here in the question. Anyway, so okay, so now let's see what do we do there. This is a very straightforward, simple problem. Actually, let me go to this screen. So we have so on and so forth. We have the first array, the second array, so on and so forth. The nth array, each array is m elements, right? So what can I do? I can merge these two. I can merge the first two, right? Think about it. I can merge the first two. I can keep merging these things. Okay, I can merge the first two. How much time complexity would it take to merge both of them? If I merge both of them, what do I get? I get an array of size 2m. And how much time it would take for me to merge them? It will take me 2m time. Right? The third and fourth. Similarly, the third and fourth I can merge. The third array and fourth array. Right? Again, I will get an array of size 2m. What is the time complexity of merging? 2m, because there are 2m elements. I can keep doing it. Right? How many merges would I do here? Since I have n arrays, look at this. Since I have n arrays, I will be doing n by 2 merges. Because I'm merging two arrays, right? I'll be doing n by 2 merges. Each merge time complexity is 2m. So what is the total time complexity to finish this first step? It is order of n into m, right? Because 2 will cancel out. Next, I'll again merge these two. I'll get an array of size 4m. What is the time complexity? 4m. Again, the next 2m's I'll again merge. I'll get a 4m. Again, what is the time complexity? 4m. Now, how many merges will I perform here? I'll perform n by 4 merges, right? Look at this. Because I have n by 2 arrays here and I'm merging two-way, I get n by 4 merges. And what is the time complexity of each merge? 4m. So 4 cancel out. Again, I get nm. This will keep going on. We have seen this in the case of merge sort also. What is the depth of this tree till the time I have just one array? We've seen this many times. We have seen this type of recurrence tree, right? We've seen this tree when we are analyzing merge sort. This tree depth, because we have n elements to start with. Look at this. First I have n, then I have n by 2, then I have n by 4, so on and so forth. Finally, I have 1. What is it? The moment you see a structure like this, you should tell me log n base 2. Right? Of course, we have shown how to prove this multiple times, right? In GATE exam or in any exam, the moment I see this structure, I immediately write log n. You shouldn't even blink an eye there, right? And for each stage, I have order of nm, right? For each stage, I have order of nm. And how many such stages are there? Log n such stages. So what is the total time complexity? N into m into log n. So let's see if that is there in our options. Okay, so n into m into log m. Yes, second option, right? So folks, the important thing is when you're practicing, when you're understanding a concept, it's good. But when you solve problems, right, you have seen this so many times. You write it as 2 power k, all of that stuff, right? It should immediately strike to you that it's log n and solve it like within 10 seconds. Okay, so this is a good question, but I hope they should have given two-way merge explicitly here. Otherwise, people like me can think of k-way merge and get confused, right? So again, let's see what happens if you have k-way merge, since we have some time, okay? If I'm doing a k-way merge, what happens? Okay, so I have to pick the smallest element from these k elements or from these n elements, right? To imagine if I'm not doing a two-way merge, if I'm doing a k or n-way merge, if I do an n-way merge, what happens? What are the total number of elements that I have? Total number of elements I have is n cross m. I have to touch, see, each element is going to be placed here. What is the total size of this? This total size is going to be n cross m, right? So for each element, how much time it takes for me to fill one element here? I have to compare n elements. I have to compare n elements and find the smallest of these n elements to be placed here. Basically, I take all of these, I compute the smallest amongst them and place it here. To compute the smallest, I require order of n time. So what is the time complexity? If I use the k-way merge, it is n into m, because I have n into m elements here. For each element, I take n comparisons. In such a case, it is order of n square m. Thankfully, that option is not given here. Okay, but I hope, of course, the moment I see that, like I can't solve this problem. But instead of k-way merge, for people like me who are biased more towards k-way merge because they've used it in the real world, if they would have mentioned two-way merge, that would have made the question much more clearer. Okay, because I actually solved this question with k-way merge. I didn't see any of the options here. Then I said, okay, I see log n here. That means some way there has to be some two-way merge. Okay, that's how I thought about it. I actually, when I solve this problem, I don't look at options. I look at the question. I wrote the k-way merge. I said, this is my answer. I don't find the answer anywhere. None of the above is also not there. Then I started seeing these terms like log n. Oh, then I said, okay, if log n and log m type of terms are there, what they mean is actually two-way merge, not a k-way merge. Because most undergraduate students may not know about k-way merge. Okay, so that's a good one. This question, again, it's a straightforward question. You'll be surprised how simple. While the question is large, it's a straightforward question, right? So let's see. I'm sorry. Okay, so let's look at this. I have n power half log n square. What is log n square? It is 2 into log n, right? What is log n square? This 2 will come out in logarithms, right? So what I have here is log n and n power half. Which of them grows faster? Obviously, n power half grows faster than this, right? Which means your g of n is equal to big O of f of n. In case one. Okay, let me change this to large, right? In case one, what do I have here? In case one, because f of n is growing faster than g of n, because this is nothing but 2 log n. So this is the right one. Let's look at this, because I'm given these pairs, right? So what am I given? Okay, let's first solve the problem. I'll come to the options later. That's what I prefer personally. Okay, because that helps me learn the concepts better. What is this? Here again, I have log n square. Again, this becomes 2 log n. Sorry, this basically becomes 2 log n. Right? Because this 2, I can remove it and place it here. And this is log n. They're the same. Right? So I can write it as fn equals to big O of gn. I can also write it as gn equals to big O of f of n. Both of them are valid. Because f of n is theta of g of n. Because I have, what do I have here? I have log n here. Asymptotically speaking, they're the same. What about the third one? Obviously, this grows faster. This is quadratic and this is exponential. We know exponential grows faster, right? The moment you know exponential grows faster, you should write g of n is big O of f of n. What about this fourth one? Obviously, 3 power n grows faster than 2 power n. Obvious, that's staring at your face, right? So f of n is big O of g of n. Now we are given some options. Let's pick what it is. Actually, I don't think I've solved it this way. Okay, what is it? Second option is, what does it say? G of n, this is true. What is the fourth option it says? Fourth option it says G of n is big O of f of n. No, this can't be true. What is this? F of n equals to, first option is f of n equals to, no, that's not true. This is not true. First option is G of n equals to big O of f of n, right? So this is right. What is the second option? It says, oh, any of them can be right? So this is the right option. That's it. So 15 questions. I mean, when I explained it in detail, it took us 1 hour, right? If you were to actually solve this, sorry.
Who wants to repeat?
Oh, you want me to repeat 10th question? So let's go through that. Okay, sure, no problem. What is the 10th question here? Oh, 10th question is the string comparison thing, right? So let me get the notes for it. Okay, so 10th question notes is this. Okay, so you have a list of n strings, each of length n, to be sorted in alphabetic or lexicographic order using merge sort. What is the worst case running time? If you think about n numbers using merge sort, okay, when you try to solve merge sort with n numbers, what is the time complexity? Order of n log n. But here, merging, when you're merging, let's assume I have two arrays here and I'm trying to merge them. I have to compare this number with this number, and I can determine if this number is greater than this number or not in order of one time. Right? That's a property of numbers, right? We never mentioned that explicitly, but that's what we are using internally. And when we're doing this, we got time complexity as order of n log n. But instead of numbers now, if I have strings, to compare two strings, you have two strings of length n. To compare both of them, which of them comes first alphabetically or in a dictionary order, lexicographic order, the way to imagine lexicographic order is the dictionary order, right? Whether Hyderabad comes before or New Delhi comes before. Okay, let's assume I have two city names, right? So H in alphabets is before N, right? So you just check these two, and after just checking these two, you can say they're both the same. Imagine if I have two names like this, Hyderabad, right? And Hyderabad 2. Let's say there is some city in Hyderabad in Pakistan also called Hyderabad. Okay. So let's call that city as Hyderabad 2. Okay. So now what happens? So this is called Hyderabad 1. This is called Hyderabad 2. Now to compare, all of them are matching. The last number is different, or the last character is different, right? So the worst case time complexity to compare these two strings is order of n. Now, which means when I'm merging these two arrays, look at this. When I'm merging these two arrays, what's happening? Instead of taking order of one time to compare, now I'll start taking order of n time for each comparison, which means my total time complexity now would become order of n square log n. Okay. So that's all there is. Anyway, this video will be on YouTube. You can always go back and see the solution. If you made a mistake or if there is a better solution, please recommend to us. Because it's continuous learning. It's foolish to claim that we know everything or you don't know anything or you know everything. All of them are foolish. We're all here to learn. So let's do that. So again, what I was saying this, right, while Naveen just told me. So in 1 hour, we solved 15 questions here with detailed explanations. With some practice, you can solve these 15 questions in like 20-25 minutes, to be honest. Okay, I actually solved these problems in my notebook and I wrote detailed notes. That took me 30 minutes, including detailed notes. If I were to do it in an exam setting, probably I think I can do it in 15 to 20 minutes. So these are easy problems. These are not rocket science. With explanations, it took. So look at it. Always look at timing, right? In the GATE exam, we have 65 questions, right? So we have 65 questions, some easy, some hard, and we have 180 minutes, right? So when you're solving questions, right? When you're solving questions for 1 mark questions versus 2 mark questions, right? Try to take no more than 2 minutes to solve a 1 mark question. Try to take no more than 4 minutes to solve a 2-minute question. A 2 marks question, because 2 marks questions are slightly harder, to be honest. And they might be more time taking also, right? So if you're solving a 1 mark question, 2 minutes is what you should try and achieve it. I'm not saying that you should do it today, but keep this in mind, because as you approach closer to the exam, you want to be able to do this. And if you can practice it from today, you have 11 months to crack it. If you can crack all the easy problems in 1 minute, slightly harder problems in 2 minutes, then time should never be an issue for you. Okay, sounds good. Let me just change the screens here. I'll stop the screen sharing. And thank you, folks. Thank you for joining us today. And it was nice solving these 15 interesting problems. And again, the next live session would be on Wednesday. And our team will send out the topics that are to be covered, and also the practice test for next Wednesday, right? So we are having these live sessions Wednesday and Saturday. This is our second live session. We'll be doing the next live session. We'll try to stick to that. Unless there is a major issue or some major disruption, we'll try to do it on Wednesdays and Saturdays. our team will send you the detailed topics that are to be covered before next Wednesday, and also the practice problems. Okay, we'll try to send it to you tonight or early tomorrow morning. Okay, folks, thank you very much. Thank you for your time. Thank you for joining us on a Saturday evening. Have a good weekend. Take a good break and enjoy yourself. Bye bye.